so this is where we're headed today, right? We want to talk about the complex logarithm. And if you think about what we talked about last week, we talked about using real logarithms to compute real exponents, right? We noticed that 5 to the square root of 2 is hard to make sense of, and the most sensible way of writing this is as e to the log of 5 times square root of 2. We talked about how this degenerates into a power series in which all that you're using is addition, subtraction, multiplication, and division, right? And so we're able to make sense of this for real exponents, and it turns out that this is the approach that we're going to use to compute complex exponents as well. So if we have z to the w, or z and w are complex numbers, the way we're going to compute this is we're going to take e to the z, e to the log of z raised to the w, which is really this here. And so this is where we're headed, and what we need to do is we need to basically define this complex logarithm, which it's really, really fascinating. And it takes some work, but it's well worth the effort. Okay. And so where we left off last week is we had talked about a special form for complex numbers. Specifically, we had discussed the idea that every complex number can be thought of as a we discussed the fact that e to the z can be thought of as e to the x times cosine theta plus I sine theta. Well, let me change the notation on that. Let me do this in two pieces. If z is a complex number x plus iy, then we can rewrite this as e to the x times cosine y plus I sine y. Okay. So this is what we had worked through last time, is that we determined that if you have e to the iy, you can write it as cosine y plus I sine y. Okay? And so this represents a direction in the complex numbers. In this e to the x, this represents a radius, a radius value. And this may not be super clear yet, but we're going to talk about the geometry of complex numbers here in a couple of minutes. I'm just recapping what we had done last time. E to a complex number can be thought of as e to the real part times cosine y plus I sine y. And so, what we have to do is talk a bit about the geometry of complex numbers. This is a really great topic in and of itself. Geometry of complex numbers, like I said, you can think of a complex number as a direction in the complex number system together with a length or a radius, okay? And so, for example, let's go and consider a couple of complex numbers. Suppose we have z equal to 3 minus 2i. Then we know that in the complex number system we've got a real axis and an imaginary axis, right? The 3 minus 2i says we're going to go out 3 units on the real axis and minus 2 units on the imaginary axis. So 3 negative 2, 3 negative 2i will be right here. Same idea, if you had something like minus 1 plus 3i. It's basically just plotting x and y coordinates, right? So we've got -1 says we're going to go up -1 in the x direction. 3i says we're going to go 3 in the I direction. And so that's the geometric interpretation of a complex number, is that you've got a real part and an imaginary part. Real part says how far to go in the x direction. Imaginary part says how far to go in the y direction. So any questions here? All right, so what you'll notice is that the rectangular form, it's pretty clean, but it has its limitations as far as calculations go, okay? The calculations in rectangular form, this is rectangular form where you think in terms of x coordinates and y coordinates, the calculations are a little bit cumbersome here. Because having multiplied complex numbers in rectangular form, you have to multiply it out like you would polynomials, right? So ZW is equal to 3 minus 2i minus 1 plus 3i. And like I said, you just multiply it out as if it were polynomial. You get minus 3. There we've got minus 2i and 1 gives us plus 2i, plus 9i, which is plus 11i. Just double check we got that right. 9i here and 2i there. And then plus 6. Okay. Well, let me write that out in 2 steps, actually. Because we've got minus 2i plus 3i is minus 6i squared, and the I squared is minus 1. Okay. So there we go. So we've multiplied this out, and we get 3 plus 11i. And, it's fine. It's basically polynomial multiplication where when you have a square, it amounts to minus 1, right? So it's fine, but it doesn't really mesh that well with what's going on in this geometric picture, right? For example, when we plot this thing, 3 plus 11i, it's going to be way out here. And how exactly does this product result from the product of the two complex numbers we started with? The geometry of how these three vectors relate may not be necessarily that clear, right? And so there's a better way of interpreting complex numbers, which is the polar form of complex numbers, right? And so this is literally just exactly what we've seen from basic calculus. How many people haven't seen polar form yet? Frank, have you seen polar form yet? Okay, good. You guys seen polar form? Good. So we're all familiar with polar form. We know that we have something like rectangular coordinates 1 square root of 3. That says go out 1 unit on the x direction and square root of 3 units in the y direction. And we can think of this as basically two, in terms of two other variables, right? We can think of this thing in terms of an angle, how far we've rotated from the positive x-axis, together with an r value, right? And so if you transform this from rectangular coordinates into polar, you express this in terms of r theta, okay? The radius here turns out to be 2, and the angle associated to this vector is pi to the 3. And so this is also a very natural way of thinking about the xy plane. Given any point, how far did you rotate from the x-axis, and how far out from the origin did you go, right? And so it turns out that this is actually the right way, not the right way, but sort of a better way of thinking about complex numbers is, a direction together with a magnitude. And so the polar form of complex numbers just that. It says we're going to write a complex number as r e to the I theta, okay? And e to the I theta is a complex number with unit magnitude in the direction of theta. Okay, complex number with unit magnitude in the direction of theta. R is the length of this complex number C. Okay. And so you put those two things together, and any complex number then can be thought of as a direction that's been scaled to the appropriate length. Okay. So in our case, if we're looking at this complex number in rectangular form, 1 plus square root of 3i, then let's go and convert this thing into polar form. It's really just a matter of, identify r, identify theta, and plug those into this polar form, right? So the radius for a complex number, remember this is, this complex number represents 1 unit along the real axis and square root of 3i units in the imaginary direction. And so to compute the length, obviously we just need the length of the real part, length of the imaginary part, and then we can just use the Pythagorean theorem, right? And so all we have to do then is the radius is just given as the square root of the sum of the squares of these. Okay? That's how far we went in the x direction, how far we went in the y direction, Pythagorean theorem to get the length, which is 2. So we've identified the r value so far, right? To identify the theta value, we can identify the reference angle for this guy. And so the reference angle turns out, you can just use inverse tangent of y over x. Arctan of square root of 3 over 1. That turns out to be pi over 3. That's just the reference angle, right? So sometimes we'd have to use that reference angle to track down the actual angle relative to the x-axis. In this case, reference angle and the actual angle coincide, right? So in this case, that's also our angle theta. And so we've, just by taking the geometry of this thing that it represents some direction in the x, some amount in the y, and just using some basic trig, we've now tracked down the two values that we needed. We've got our r value, we've got our theta value. And so that complex number, 1 plus square root of 3i, is really the same as 2e to the I theta. So that's the polar form of this complex number. And so, just to make things hopefully even more clear, living inside this vector is a vector of unit length. So this blue vector here, this thing has unit length, and that is that e to the pi over 3. Unit vector in the direction of pi over 3. And then we just take this thing and rescale it by a multiple of 2. And when we rescale it, we get exactly the vector that we needed. Okay, so that's sort of a more natural way of thinking about complex numbers. A direction, complex direction that's been scaled to the right length. And so, just a brief little proof that this really does give us what we think it's giving us. Let's take a look at, so so far I've just told you guys that re to the I theta, it really is, what we think it is. It's a vector at angle theta with radius r. But to verify that re to the I theta really does have length r and direction theta. I'm not sure if there's I'm sure there's a nicer proof out there. The one that I wrote is a little bit confusing. But, we'll work through it anyway. So to verify that this thing really does have length r and really does have direction theta, what we'll do is let's set up a vector v at direction theta and length r, okay? So maybe we have this vector v, and maybe we assume that it has angle theta and radius r, okay? Then what you'll notice is that just by basic trick, we can decompose this thing into an x direction and a y direction, okay? And so v, we can think of it as, we're assuming it has length r, right? And so we can think of v as r cos theta in the x direction. How should we denote? So think of x hat as just a unit vector in the x direction, okay? So v is r cosine x, so the projection of this thing onto the x-axis in this direction, plus r sine theta y hat, where y hat is a unit vector in the y direction, okay? So here's our x hat and our y hat. This says v, you can decompose it to an x direction, y direction. By taking r cosine theta, that's how much is in the x direction. R sine theta, that's how much is in the y direction, right? And let's go and just take a look at r e to the I theta. We demonstrated last week that e to the I theta is really cos theta plus I sine theta. Distribute the r through. And what you'll notice is that we have a secret 1 hiding right here. So we've got r cosine theta times 1. R sine theta times I. And so in the complex world, you'll notice that those are exactly those unit vectors that we talked about, right? 1 is the unit vector in the real direction. I is a unit vector in the imaginary direction. And so what is this equal to? This is the projection of v. The projection of v into the x direction. And this is the projection of v in the x direction plus projection of v in the y direction. And so we see that re to the I theta is really just, this is just v, right? This says take the x component of v plus the y component of v, so you just add those things together, you just get v back, right? So this says that re to the I theta is really the vector v, which we assumed had radius r and angle theta. So that's just a verification that, yeah, that re to the I theta, it really is the vector with angle theta and size r, right? So like I said, a little bit confusing, but it's not of any, real big consequence for what we're going to talk about later. And so, I've told you so far that, we're using this as a quote-unquote more natural way of thinking about complex numbers. And so naturally we'd like to see why this happens to be the more natural way of thinking about them. And to see that, let's go ahead and take a look at how these things multiply. Has anyone seen multiplication of complex numbers before and what it represents? No? So this is new territory for me? Good. It's really interesting. Multiplication of complex numbers consists of two operations. First, multiplying the radii of the complex numbers, and second, it amounts to adding the angles. So multiply the radii. Add the angles. And for those of you guys who weren't here last week, just a FYI, there's two other words that we often use for these. So radii, we often call those the modulus, or we may say norm as well. And so these three terms, they all mean the same thing. Radius, norm, modulus, all the same thing. The angles are what are called the argument. And so I'll sometimes use those terms interchangeably. Angle, argument, same thing. So multiplication consists of multiply the radii and add the arguments, the angles. Division as you might guess, consists of divide the radii and subtract the angles. Let me try out our new terminology here. Divide the modulus is moduli, and subtract the arguments. And so this is sort of the point of polar form, is that the operations in the complex world, they're most naturally thought of in terms of rotations and rescalings, right? And so obviously rectangular form doesn't mesh that well with that interpretation. And so the polar form is much more natural, right? So let's go ahead and take a look at how the polar form gives us these interpretations. So if we have two complex numbers, we'll call them z and w. Z will be r1 e to the I theta, and w will be r2. Let's do theta 1 and theta 2. So there's two complex numbers. Then it's literally this simple. ZW, we're just multiplying, right? So what happens here, we get the product of the radii. And when we multiply e to the I theta 1, e to the I theta 2, you just add the angles. And so in polar form, what looks like a somewhat exotic behavior, right, multiply the radii, add the exponents, it just falls out immediately from the polar form, right? Same thing with the quotient, z over w. Z was r1 e to the I theta 1. W was r2 e to the I theta 2. And so, r1 over r2, that's the quotient of the two radii. e to the I theta 1, e to the I theta 2, same base, so we can just subtract those exponents. We'll get e to the I theta 1 minus theta 2. Oops. Questions there? So I thought we'd maybe go over a couple of examples. And suppose we have a complex number 5 minus 5i, and w given by 1 plus square root of 3i. And we'll do this two ways. We'll set it up, with the rectangular form. Do it that way, and we'll also multiply it with the polar form. So if we want the product, CW, then in rectangular form, like I said, basically amounts to multiplication of polynomials. So multiplying this out, we get 5 minus 5i plus 5 squared root of 3i. And then multiplying these together gives us minus 5 squared root of 3i squared. And then, of course, I squared ends up giving you a positive there. So you get 5 plus 5 squared root of 3. And then this term here can't really be simplified. Okay. So there we go. Multiply out the numbers in rectangular form. That's the real part. And the imaginary part. And so, the multiplication is straightforward, but if you had to tell me where does that complex number live, not necessarily that clear. And how does this complex number relate to the two values that went into it? Again, not that clear. So the more natural way, like I said, is to use polar form. And so the hardest part about multiplying things in polar form is that you have to find it first, right? And so to find polar form, you have to go through those same routines that we did before. We need the radius. The radius for a complex number says just take the square root of the sum of the squares of the components. So that'd be 5 squared. It's negative 5 squared, and that gives you 5 squared root of 2. The angle, we have to use that inverse tangent business, right? So we can see where this thing's going to live, right? The real part is positive, imaginary part's negative, so it's going to be down in this region here. 5, negative 5i. So here's our complex number here. And so we can identify the reference angle here by taking arctan of the absolute value of the ratio of the components. So the y component here is minus 5. X component is 5. And the inverse tangent of 1 we know is pi over 4. And And that's just the reference angle, right? So the reference angle is pi over 4, and so what would the actual angle be relative to the x-axis?
Pi over 4?
Negative pi over 4. Yeah. So this angle here, that's our angle. And so there we go. We've identified the polar form. Radius is going to be pi squared root 2, and the angle is negative pi over 4. So there we've got the polar form for the first number, and then the polar form for the second number. 1 plus square root 3i is going to be here. You'd run through that same routine. We actually did this one earlier. Square root of the sum of the squares of the components gives you 2. And then arctan of the ratio of the absolute value of the components gives you 5. Okay. So we computed the polar form for each of these things. So multiplication just amounts to polar form for z. That's going to 2e to the negative pi over 4i. And polar form for w, 2 e to the pi over 3i. And so multiplying the radii gives us 10 square root of 2. Multiplying the angles gives us e to the, let's see, pi over 3 minus pi over 4, because that's going to be pi over 12. I did this earlier, so I think that's what I got. Let's see. Yeah, pi over 12. So assuming I did it correctly earlier. Okay. So there we go. We've got our answer expressed in terms of polar form. And so, e to the pi over 12, that's a unit vector in the direction pi over 12. E to the pi over 12i, rather. And we're going to rescale that by a factor of 10 square root of 2. So it'll be out to a length of about 14 point something, right? 14.1 or something like that. So there we go. And so now it becomes pretty clear what's happened between these vectors, right? So here's the first vector that went into it. 5 minus 5i. Here's the second vector. And so, yeah, we see exactly what happened. Add these two angles, what do you get? Negative angle here, large positive angle here. They add to something a little greater than 0, pi over 12. And multiply these radii, end up way out here at 10 square root of 2. Questions there? And I've got another example that we could work through. It's a little bit messier, which I did just for fun, really. But I think we'll push on. If you guys want to see another example later on, we can work through it. And so this is what we need in order to set up logarithms. So we need to be able to interpret exactly what the geometry of complex numbers is. And then setting up the log is going to be relatively straightforward, I believe. Okay. And so let's go and just think back to what we normally think of as a logarithm, right? So what is a log? Oh, by the way, I always write log for log base e. I don't usually use ln, so whenever I write log, it's log base e. So whenever we think of logarithm, what we're thinking of is the solution to this equation, right? Log of a is the solution to the equation above. Right? It asks e to what power gives a? And so, what we're going to do to determine what this complex logarithm is, so a here is a complex number, z is a complex number, right? To write this logarithm, what we're going to do is we're going to take e to the z, and we're going to express it in two different forms. We're going to express it in terms of its, where z is in rectangular form, and we'll also express e to the z in terms of its polar form. Okay? We're going to write e to the z as e to the x plus iy. Okay, so we've written z in its rectangular form. And when we compute this exponential, we're going to get some complex number, right? So what we'll do is, pretend like we've computed this complex number. We're going to write the answer to this exponential in its polar form. So whatever value this has, it has some r value, r, and it has some angle or argument, theta. Okay? So we compute this value and express it using its polar form. And what you'll notice is that, okay, we saw earlier that this e to the x plus iy can be written in the following form as e to the x, e to the iy. And if that's equal to this r e to the I theta, then what you'll notice is that we can pretty much just match up pieces here, right? We see that this real term here, let's go ahead and match it up with this radius value r. And this imaginary term here, the complex direction here will match up with the complex direction there. And so, what we see is that to get e to the x to match r, we're just asking this question: what should x be? To get e to the x to match r. And the answer to that is just the regular log of r. Right? Log base e, right? Because when we plug that in, e to the log of r, the e and log just cancel one another to give you r back. Okay? So to solve this equation, x just has to be the log of the radius. And so we've taken care of this first value here. Same thing here. How can I get these two values to match? Well, these two values, they'll certainly match when y is equal to theta. And so what we've done is we've basically constructed a very important part of the complex logarithm, okay? Because what we've done remember that the logarithm is going to be the solution to this equation, e to the z equal to a. What we've done is we said in the solution to this equation, as long as z is equal to the log of the radius for a plus I times the angle for a, then we've done our job. Right, if we make z equal to log of the radius of a plus I times the argument of a, then let's raise e to the z. What happens here, we can split this up as e to the log of the radius of a times e to the I times the angle for a e to the log of r of a, the e and log just cancel one another to get you the radius of a, and e to the I argument of a gives you, this one you can't really simplify that much, but its geometry should be clear. E to this value here has given us the radius that we need for a at the direction that we need for a. Therefore, e to this value is a, right? The radius we need for a times the direction that we need for a. So this guy right here is the solution to the equation e to the z equals a. And so this guy right here is one version of the complex logarithm. And it kind of seems like we're done, right? Because, had you solved that equation, you identify the radius for a, identify the angle for a, and then just plug them into this expression here. That gives you a solution, right? And so we are mostly done, but what you'll notice is that this solution is actually not unique, right? And to illustrate that, let's actually take a look at an example. It's not unique. And to get a sense of how this thing fails to capture all the solutions, like I said, we're going to take a look at an example where let's compute the log of 3 square root of 3 plus 3r. Okay. Well, we've seen already that all we have to do is take the log of the radius plus I times the argument to this thing. I'm going to write it like this. Yeah, that's fine. Log of the radius plus I times the argument of this complex number. Okay. And so to compute this log, we just compute these two things separately. Okay. The radius of this complex number, like I said, it's just the square root of the sum of the squares of the components. That gives you, what is that, 27 plus 9? Is that right? Yeah, 27 plus 9, so that gives you 6, right? Square root of 36. So there's the radius, and we've taken care of this piece here. Okay. Now we need the argument, or the angle, for this complex number. It's at 3 square roots of 3 and 3. And so we know that to compute the argument, take the inverse tan of the absolute value of the ratio of the components. You compute that inverse tangent and you get pi over 6 for the reference angle. And because we're in the first quadrant, the reference angle matches the actual angle relative to the positive x-axis, right? And so, like I said, we've just computed these things. So we take, to compute this logarithm, we take log of radius. This is the real logarithm here. Plus I times the argument for that angle, pi over 6. Okay. And so, let's go ahead and just verify that this is actually the logarithm that we wanted. E to this logarithm, this log here, this is the real logarithm. What does it give us? What does it give us? It gives us e to the log of 6 times e to the I pi over 6. This thing is 6. This thing is cosine pi over 6 plus I sine pi over 6. And that degenerates down into cosine pi over 6 is, yeah, square root of 3 over 2. Sine pi over 6 is 1/2. Multiply that through, and lo and behold, we get exactly what we wanted back. And so this is all motivating the idea that there's only, that we've only gotten one solution. We're hot on the trail, so we've got one solution, but I keep talking about more possible solutions, right? And so the basic idea behind where these other solutions are going to come from is that, suppose that we have I pi over 6. What if we add 2 pi to that? We circle all the way back around. Then we're going to end up at the exact same place, right? So now we've found one solution right here, but let's go ahead and add on multiples of 2 pi I. So that now we're saying the logarithm of that number really instead of just that single solution there, log of the radius plus pi over 6 for the argument. If you add on any multiple of 2 pi I, where k is an integer, that's also going to give you a solution, right? Oops, sorry. This is also a solution. Because e to this value, I'm going to skip a few steps here because they're kind of boring. E to this number here is really 6 times cosine of this angle pi over 6 plus 2 pi k plus pi sine of pi over 6 plus 2 pi. And cosine and sine, what's the period for cosine and sine? The period? Yeah, period. 2 pi.
2 pi?
2 pi, right? If you add on multiples of 2 pi, you just get the same function back. And so if you add on any multiple of 2 pi k onto that original solution, add on multiples of 2 pi k, you get the same solution back. And so the full-on solution to that exponential equation is log of r plus I argument plus 2 pi I k is the final solution. 2 pi I k gets tacked on there. And that gives you all possible solutions. Man, that hour went quick. I'm kind of bummed. There's so much more I wanted to talk about today.